This is the 4.5, 4.6, 4.9 review problem number 1, part A. We're asked to find the limit as x approaches 0 of e to the x minus 1 over sine x. So the first thing I'm going to do is check and see what would happen if I were to plug 0 into this limit. And on the top, I would have e to the 0 minus 1. E to the 0 is 1. 1 minus 1 is 0. On the bottom, I would have sine of 0, which is 0. So I end up with 0 over 0, which tells me that I can use L'Hopital's rule. So when I do L'Hopital's rule, I will be taking the derivative of the numerator and the derivative of the denominator. The derivative of e to the x is e to the x. The derivative of negative 1 is 0. In the denominator, the derivative of sine x is cosine x. And now I am going to check to see what I get when I evaluate my limit this time. And e to the 0 power is 1. So I know that because I have 1 in my numerator, that whatever I get here in my denominator is going to determine my answer. And cosine of 0 is 1. And so the answer to my limit, 1 over 1, is equal to 1. In part B, this one is a little bit more complicated. I have the limit as x approaches infinity of e to the x over x cubed. So this time when I check my limit, e to the infinity power is going to be infinity, and infinity cubed is going to be infinity. So I have infinity over infinity, which tells me that I am able to do L'Hopital's rule. So this will become the limit as x approaches infinity. The derivative of e to the x is e to the x. The derivative of x cubed is going to be 3x squared. Then I check again. But in my numerator, I still have e to the infinity, which is infinity. And in my denominator, I have 3 times infinity squared, which is still infinity. So once again, I am going to need to do L'Hopital's rule. So then I get the limit as x approaches infinity. The derivative of e to the x is still e to the x. The derivative of 3x squared is going to be 6x. Now I check again. E to the infinity power still gives me infinity in my numerator. 6 times infinity still gives me infinity in my denominator. I still have an indeterminate form that allows me to use L'Hopital's rule. So I'm going to do it one more time. But this will be the last time, because as I do the limit as x approaches infinity, the derivative of e to the x is still e to the x. But in my denominator, the derivative of 6x is just 6. And now that I have a number in my denominator, I know that this will be the last time that I do this. So now when I plug in my values, in my numerator, I get e to the infinity, and in my denominator, I get 6. E to the infinity is infinity. Infinity divided by a number still gives me a result of infinity as the answer to my limit. Part C, we have a function where we have a function raised to a function. This is one of those situations where, first of all, when we plug 0 in, we are going to get 0 to the 0 power when we check this. Okay, so that's one of our indeterminate forms where we're going to have to use the natural log of both sides to try to rewrite this so that we can get to a point where we can use L'Hopital's rule. So the first thing that I'm going to do is I am going to let y equal the limit as x approaches 0 from the right of x to the tangent x power. Okay, so I'm going to start my problem by calling my limit y. So now I have y equals this limit, right? So my first step then is going to be to take the natural log of both sides of the equation. So I will have natural log y on the left is equal to natural log of the limit as x approaches 0 from the right of x to the tangent x power. And I know that the natural log of the limit is the limit of the natural log, so I can move that natural log to the position in front of the x, which is what I want to do so that I can use the properties of logarithms to bring that tangent down out of the exponent. So in the next step, I'm just going to rewrite this as natural log y is equal to the limit as x approaches 0 from the right of the natural log of x to the tangent x power. And as I mentioned, in my next step now, I'm going to use the properties of logarithms that say that the exponent on something inside of a log can come down and become the coefficient of the log. So now I will have the natural log of y is equal to the limit as x approaches 0 from the right of tangent x times natural log x. And then when I get to this point, I'm getting closer to where I want to be so that I can use L'Hopital's rule. But again, to use L'Hopital's rule, we need a quotient, right? We need an indeterminate quotient. So how can I rewrite tangent x times natural log x as a quotient? Well, multiplying by tangent is the same thing as dividing by cotangent, right? So I could rewrite this as natural log y is equal to the limit as x approaches 0 from the right of natural log x divided by cotangent x. And now, if I check what this limit would be equal to currently, where I'm at in the problem, if I plug 0 in from the right, ln of 0 goes to natural log, or ln of 0 from the right, excuse me, goes to negative infinity, and the cotangent of 0 goes to, from the right, goes to positive infinity. Okay, so I have infinity over infinity, which is one of our indeterminate quotients that allows us to use L'Hopital's rule. So I will still have natural log y on the left side of my equal sign, but on the right, now I am going to apply L'Hopital's rule. So I'm going to take the derivative of the numerator and the derivative of the denominator. The derivative of natural log x is 1 over x. The derivative of cotangent x is negative cosecant squared x. And then I'm just going to do a little keep switch flip here. Or actually, what I'm going to do is dividing by cosecant squared would be the same thing as multiplying by sine squared. So again, I am just doing a little rewriting. I'm not doing any calculus at this point. So this is the limit as x approaches 0 from the right. So I'm going to have 1 over x times, and then again, if I'm dividing by cosecant, that would be the same as multiplying by sine. I keep the negative. So I've got a negative sine squared x in my numerator. Okay, so I really have negative sine squared x divided by x now. So let's check and see what our limit would be equal to at this point. So if I were to plug in 0, sine of 0 is 0, 0 squared is still 0, so my numerator would go to 0, and then my denominator is x, so that would go to 0. So once again, I have a situation where I would need to do L'Hopital's rule again, another time. So coming up here, whoops. I am going to apply L'Hopital's rule again. Still have my natural log y on the left, but on the right, I am going to have the limit as x approaches 0 from the right. So now in my numerator, I have the negative sine squared x. That is what I am taking the derivative of. So we have to think of this, I'm going to write it here back below in the last step, as negative sine x quantity squared, okay? So when I take the derivative here, this is going to require us to do chain rule. So we would bring down the 2, and that would become negative 2 times sine x. But then we have to multiply by the derivative of sine x, which is cosine x. And then our denominator, the derivative of x, is going to become 1. So we know now that this is the last time we will have to do L'Hopital's rule because we have a 1 now in our denominator. So in my next step, I'm going to go ahead and I am going to evaluate this limit. So natural log y is equal to negative 2 times sine of 0 is 0, and cosine of 0 is 1, divided by 1. So I end up with negative 2 times 0 times 1 is 0 divided by 1, and 0 divided by 1 is 0. So I find out that natural log y is equal to 0. Okay, now I'm not done, remember, because I called my limit y, and then I took the natural log of both sides. So now I need to go back, and I need to undo that natural log with a base of e. So I am going to raise both sides to a base of e. And on the left side, the e and the ln cancel, and I get y equals e to the 0. And we know that anything to the 0 power is 1, so y equals 1. Which, remember, y was my limit. So y is equal to the limit as x approaches 0 from the right of x to the tangent x power, which we now know is equal to 1. So that is the answer to our limit for part C. In part D, this one is a bit of a trick problem. We are doing the limit as x approaches pi from the left of sine x over 1 minus cosine x. Make sure that you check before you apply L'Hopital's rule, because guess what? If we do direct substitution, sine of pi divided by 1 minus cosine of pi, well, in my numerator, sine of pi is equal to 0, and in my denominator, cosine of pi is equal to -1. So I have 1 minus -1 in my denominator, which gives me, chop, chop, 0 over 2, which is an answer of 0. So this was not an indeterminate form to begin with. Therefore, we did not need to and shouldn't have done L'Hopital's rule. We could evaluate this limit immediately doing direct substitution. Just make sure that you always check before you apply L'Hopital's rule.